Welcome to TennaTalk, a journey of discovery about all things antenna. TennaTalk is a production of the Antenna Whisperer. That's me, Rudy Wiedemann, K7RAW, and generously sponsored and supported by the Las Vegas Radio Amateur Club. This podcast for Bravo is a companion podcast to one about impedance matching. Here we're going to be talking about driving SimSmith. 4 Alpha was all about laying the groundwork of how to do impedance matching using LC circuits on a Smith chart, and we'll actually do it live with SimSmith and teach you how to do it on your own. So what can you do with SimSmith charts? Smith charts will allow you to analyze imported S1P files from a Nano VNA or EasyNet. It'll allow you to tune up antennas, either single band or multiband. You can design optimal ununs for off-center fed or end-fed half-wave antennas. You can determine the ATU tunable range of an antenna. You can design custom LC networks for tuning antennas. You can design custom circuits of all types to process any arbitrary RF signal, and much, much more. So, in the live SimSmith demo, we're going to teach you how to download and configure it to begin with, get you going, give you a quick orientation, and then we'll do some examples with simple fixed impedance resonance with low resistance. We'll do a imported file of a mobile whip model of an off-center fed with an unun, an off-center fed with an LC network. And finally, we'll auto-tune the system with the built-in auto-tune solver tool in SimSmith. And then we'll talk a little bit about exercises for you to do on your own offline to really lock in some of these concepts. So as a quick refresher, you may recall in 4 alpha the Smith chart with different path solutions depending on where you're starting from. If you're starting from the equator, which is a pure resistance and it's resonant, no impedance, neither positive nor negative, then what will happen is you will, let me turn on the pointer here real quick. Here we go. Okay, so 10,0 is pure resistance, no positive or no negative reactance. But it's not 50 ohms, so it's going to have an SWR of 5 because it's 10 divided into 50, our characteristic impedance. And you may recall you have to take different paths of different configurations of L's and C's, inductors and capacitors, to get from where you're starting from to where you're going to. Up here is a set of useful reminders of the circle path conventions in terms of whether you're operating on a resistance circle counterclockwise or clockwise, or you're operating on a conductance circle clockwise or counterclockwise, and what kind of a device you use and what orientation you put it in. Remember that we are adding components from the antenna towards the rig at all times. We want to use the fewest components to solve the impedance. We want to use the shortest path to get the lowest LC values. And then we want to watch the power degradation at each stage. We want to look at the bandwidth within different bands. And we want to analyze multiple frequencies and LC values. So as a quick reminder, we have some diagrams here that just remind you that different circuit configurations of L's and C's, or C's and C's, or L's and L's, will allow you to take different paths from your starting point to your characteristic impedance 50 ohm solution. So something to keep in mind. Now, how best to learn these concepts? Well, I recommend that you start by just reviewing podcast 4 alpha until you're comfortable with the concepts. And then watch this podcast a few times. Don't try to do anything with SimSmith, just sit back and watch. and get a feel for the concepts. Once it starts becoming comfortable, then Google search for SimSmith downloads. You'll see the first hit should be AE6TY, his website page. And I want to give a special thanks to Ward Harriman for building SimSmith and developing it over the years. It is a phenomenal tool, as you'll see, and I haven't even plumbed all the depths of it yet, but it is a tremendous contribution to ham radio, and I want to thank him tremendously for that. So download the last file on the page marked Windows 64 with jre.exe if you're a PC person. I think you can probably find the Mac version there as well, but we'll assume it's the Windows version. And then set up SimSmith, and you'll see how to do this here shortly. For a frequency starting point of 14.2, which puts you in the middle of 20 meters, with a range of 13 to 15 megahertz, which brackets 15 or brackets 20 meters. And we'll start with a fixed impedance load of 10 and a J0 or zero reactance and resistance of 10. We'll drive SimSmith around to get familiar with the environments, and then we'll work through some exercises at the end to reproduce the lessons. And then please write your questions and comments in YouTube for the video. I'd love to hear what you think. I've spent many, many days putting all this material together and recording it to share the power of SimSmith with you and to give you that power and give you that incredible tool to let you now step through that window of the whole world of impedance and antenna matching and actually start to get control of your antennas. So what we'll do with SimSmith analysis, we're going to use typically these frequencies for the center of the the 5 bands, 80 meters, 40 meters, 20 meters, 15, and 10, just as a starting point. We'll use SWR circles of 1.5, 2, and 3, which are pretty useful. And then we'll start with some fixed impedance, and then we'll do some real designs, including a 102-inch whip, an off-center fed dipole, and an end-fed half-wave antenna. So let's get going. Let's drive SimSmith. So if you bring up SimSmith for the first time, this is what you'll see. You may notice on the upper left-hand corner a little window here. Just click on the corner of it and go ahead and close that. It's just a file loader that just comes up with SimSmith automatically. So what you're looking here is at the Smith chart on the right half of the screen. You'll see in light red, you'll see the resistance circles, and in light blue, you'll see the conductance circles here. You'll see our characteristic impedance is already set at 50 ohms because we've set it here as 50 ohms. We've started with 14.2 megahertz is already in there. And I want you to notice these two blocks up here in green and in blue. The L is the impedance of the load, which is our antenna. The G is our generator or our rig or our nano VNA. And you can see the SWR here. Don't worry about the gamma. The gamma is a mathematical tool used for calculating other things besides SWR. You'll see a resistance here and a reactance. The resistance, there's a default resistance and reactance. This is where we're going to put in our fixed impedances here. Down here, I want you to take a look at the frequency range from 3 to 30 megahertz. This is in megahertz. The default is to have this as our sweep. We have not loaded any external S1P files, so there's nothing in here, no file here, and no sweep engaged. These down here are our tool blocks to add between the generator and the antenna, and we always add them from the antenna towards the rig or towards the generator, and that's how our paths proceed, as you may recall in 4 alpha. Now down here you'll see a few things, and I've already set up the SWR block to 1.5 space 2 space 3. And that sets our SWR circle. So any solutions that we get to that are within these circles give us an SWR of 1.5 or better, 2 or better, or 3 or better if they're within that circle. One last thing is, if you click here anywhere on the Smith chart, you'll notice on the lower right-hand corner, it instantly gives us an inspection of that location's Z, all right? Both the SWR and very often the frequency, but right now the Z is 10 and minus 1.36J. If I try to go very close to the equator, it'll be very close to 0J, very close. So that's just an inspection tool with my mouse click. So let's get going and have some fun. So we're going to change this to 10 ohms and 0 reactance. So that puts us right here, okay? If I move my inspection tool, you can see that this is the load right here. If it's not a file, but if it's a single load point, which is what we're using right now, you'll see a single blue circle and a cross. But if it's a file with a range of impedances, like you would get from a nano-VNA scan, you'll see some kind of a curve with this at the circle and cross at the uh, test frequency of our generator. So now, as you may recall, we have to solve this and get this impedance matched up to go to our characteristic impedance of 50 ohms. And how do we do that? Well, as you may recall, we want to take an LC circuit. So let's just try something. Let's try a series L component to begin with. And we can hover over this and use our mouse wheel and notice the blue circle over here. That's our point of frequency. And what we want to do is we want to bring this blue circle down to a conductance circle that will take us down to 50 ohms within my next component. So again, let's go here. Let's bring the bubble down to that conductance circle. Okay, so we're halfway there. And notice that this is a green path, and this block is marked with a green color to it. So we can organize and correlate our paths to our components. The next thing we want to do is we want to add a shunt C. And as you may recall, a shunt C will take us counter or clockwise down a conductance circle. And then we can click on this, hover, and we can bring the blue circle down with scrolling our mouse. And bingo, there you have it. And what I want you to notice is look at our SWR change. As I scroll the C up and down, let me click on the C. I want you to notice that the SWR is changing. And if I back off the capacitance and I put the bubble right on the 1.5 SWR, notice this is close to SWR of 1.5. So let's going to continue down here. And now we have a nearly perfect match. So the next thing I want you to observe is the power. I'm injecting 1 watt from my generator into this first component. It's injecting 99.9% of that into the next component, pretty efficient. And what's going into my load is 98.9%, pretty darn efficient. Of course, I've got a very simple case here, but you can see that we're solving this. Now the blue circle is actually the scan of solutions on the Smith chart at different frequency, on the range of frequencies from 3 to 30 megahertz. So because we're analyzing this in 20 meters, let's bracket this from 13 to 15 megahertz and notice what happens to the blue arc. The blue arc is now within the SWR 1.5, okay? So that means I've got a bandwidth of 13 to 15 megahertz all within 1.5 SWR. Now if I click down here on this block, this square, I see that indeed, here's my 1.5 SWR. I'm well below that from 13 megahertz all the way to 15 megahertz with my center of the bubble at 14.2 megahertz that you can see right here. Now, this bar indicates the ham band for 20 megahertz, which is of course 14 to 14.35 megahertz. And you can see where we are in our curve and our target frequency bubble relative to the 20-meter band. If I zoom this out to 3 and 30 megahertz, you can see a nice curve here, and you can see the stripes for 80 meters, 60 meters, 40 meters, 30 meters, 20 meters, 17, 15, 12, and 10 meters. And so this is an ideal case, of course, but now you can see that you have a really a nice curve. So what if we go the opposite direction? What if we go, first we go down with a C component and then we go up with an L component. So let's reverse these and let's rotate this and let's rotate this. And now we can go from our target, we can go to matching up our green curve to match our conductance circle, but we're going to go counterclockwise up the conductance circle with the inductor as the second component. And again, let me limit this from 13 to 15 megahertz. And again, you see we have a very nice solution. And again, if we move out here from 3 to 30 megahertz, you can see the curve. But the curve now, it has changed. It's a mirror image of the curve, the SWR curve that we saw originally with the other solution. So this is a very nice way to solve LC circuits. Okay, so let's try another one for fun. Let's go ahead and put in something that's closer to, say, 200 ohms. And it's on the equator, so it's no reactance. But now we're over here. All right? Well, let's just say 250 just to make it kind of a mirror image, because we had 10 over here to start with, which is an SWR5. Let's start with an SWR5, but on the other end of the Smith chart, and see if we can solve this and get this to 50 ohms. So we want to probably go up here with an inductor. All right, that's our purple trace, and we'll back our purple trace so that the tip of that, the end of that, would be right up here. And then we've got our series capacitor, and we're going to use that and bring that bubble down. Oh, look at that. We're on the wrong curve. So I have to back this to the correct curve, back up my L, my inductor, scroll my inductor over here, the purple device, and now I can come down to my 50 ohm characteristic impedance. And at this point, I can move to 13 and 15 megahertz, and I can look at my SWR curve. I can see I'm right in the middle, and if I want to inspect it at 3 to 30, I can do it like that. And you can see I get a very similar solution coming from the other side of the Smith chart to begin with. So that's a couple of ways of solving the fixed impedances. So now let's have a little bit of fun, because I'm going to assume that we have a fixed impedance of a 450 ohms, and let's give it some reactance. Let's give it 100 ohms of reactance. Okay, well, that's not a lot. Let's give it 1,000 ohms of reactance. All right, that's even better. So now we're starting on a reactance curve, which is one of these horns, of 1,000. Okay, we're out here at 450 ohms. This is kind of like a off-center fed antenna at the 20% point, and we're analyzing it at 14.2 megahertz. All right, so let's zoom in to 13 to 15 megahertz as our frequency range. That'll help. And now let's solve this guy for our appropriate curve. Let's bring this guy back. Let's bring him back. And let's bring him up. And we can see that we're tracking this right circle right down to our characteristic impedance. Let's tweak the inductance just a little bit, bring him in a little tighter, and bring the capacitance down. Oop, too tight. I want to get him right nailed on the characteristic impedance. So I need to open up the curve a little bit and then we'll come back down on. There we go. Nice SWR, 1.011. I'll take that. So what we've just done is we've now solved with an LC circuit the impedance of a not so unusual impedance point at 14.2 megahertz of an off-center fed antenna, 450 ohms and 1K J ohms of reactance to start with. And if we look at our curve here, it's a pretty nice solution. Not quite as nice as before. If we go 3 to 30, you can see it's a lot narrower because we have reactance we have to dial out. And the more reactance we have to use, that we're starting with, and the larger the LC values we have to use, the narrower the bandwidth is. And generally, for the same LC values, a solution will be smaller bandwidth, and will for lower bandwidth, for lower frequency bands, the L's and C's typically go up and the bandwidth goes down. And conversely, if you go up in frequency, I can use smaller LC circuit components and the bandwidth goes up and wider. Okay, so that's a lot of fun. But is there another way to solve an off-center fed dipole? Okay, so let's drag and drop these into our garbage can here, these two components. And let's see if we can solve it another way. Let's go back to our Smith chart. And let's go back, let's leave it at 3 to 30. I like to start off with a wide frequency range and zero in, because you never know what you're missing. If you're in a narrow frequency range, your solution may be outside that frequency range and you'll never know it. So again, we're starting here with the same 450 ohms and the same 1K J ohms. And that puts us right over here. Well, we could use what's called an unun. We drag an unun here. We click on the word coupled until we see auto. And the auto is a auto transformer or an unun. And now I'm going to take this impedance, and you can see this is a coil here. I'm going to reduce this down to around 1 microhenry. Let me bring it down to 1 microhenry. We're getting down there. We're getting closer. Because you'll see that I'm going to use the ratio of the input versus the output to be able to easily see what kind of ratio we want to use to solve this. Okay, so you can see that when we have reactance in here, we're having a hard time solving this. We have to go, and it's not really getting us to 50 ohms. Let's pretend for a second that we have zero reactance and see how this is much easier to solve with close to zero reactance. Aha! Look at this. Now I can back this off and I can get a little closer to my 50 ohms, but I'm not quite there yet. Okay? So what can I do? Well, I can add a shunt capacitance between the generator and the unun. That is the input to the unun, going from the rig to the unun. And now I can tweak that up a little bit, and that's a series capacitance. That's not getting us where I want to be. Let's try excuse me, that was a shunt capacitance. That's a series capacitance. Ah, that looks better. So now we're getting close. Look at that, we're getting closer. And now all I have to do is change the ratio of my unun a little bit and bring that back here to so that the green circle gets closer to my target point, and lo and behold, I'm well within the 1.5 SWR. Now if I change my primary coil, I can actually do a little bit better. I can get it right on that resistance circle. I can change the capacitance and get it nailed pretty much right on. SWR of 1.0. Now let's take a look at the efficiency. 1 watt to 99.96 to 99.93. Not bad. And if I want to inspect the bandwidth in the 20-meter band, look at that. It's a lot narrower now. Okay, so now from 13 to 15, I have a bandwidth here. Okay, but it's actually very nice. Now if I go to the full 3 to 30 megahertz, look at that. I get a nice unun that gives me a very wide frequency range from SWR 1.5 or less, from 30 meters all the way up to 10 meters and beyond. I'll be below 1.5. So here's where I can use a nice unun with a modest size capacitor, 300 picofarads or so. Now I want you to notice something interesting. Look at this. This is the ratio, 6.77 to 1.16. That's a ratio of about 6.5. Now, can you buy an unun of 6.5 off the shelf? I don't think so. But can you wind one? You certainly can. Just remember that the impedance ratio that you're looking for, in this case, it's 6 or 6.5 to 1, is going to be the square of the turns ratio on your unun. So that was a lot of fun. Let's have some more fun, and let's get rid of these components. I can just right click and delete. That's another way to rotate or delete these guys. Okay, and now you can see, by the way, when I have no components in there and I've got a generator or a nano VNA that's looking into a 450 ohm pure resistive load, pure resistive, no reactance, at 14.2 megahertz nominally, I'm getting about a 9 to 1 SWR across the entire HF band, totally flat. Why is that? Because guess what? 450 ohms divided by 50 is 9. Exactly. So that's why I would have a 9 SWR. And so it's an interesting place to start. So now what I'm going to do is I'm actually going to drag and drop into SimSmith an off-center fed dipole designed from EasyNet. It was designed at 20 meters. It's 33 feet long. We're feeding it 20% off from the end point, and it's up at 16 feet. I'm going to literally drag and drop this into SimSmith. Let me try dragging and dropping this now. Oop. All right, let's try this again. Okay, so let's try this again. Let's try dragging and dropping. Okay. I'm having a little challenge here dragging and dropping. So, oh, it's in there. Ha. Okay, I just wasn't waiting long enough. So now you can see we're looking at a scan from 3 to 30 megahertz and not bad. Okay, we're already starting to see dips in the 10 meter, near the 15 meter, close to the 20 meter, and close to the 40-meter bands. But we'd sure like to do a lot better than that. If we look at the Smith chart for this, you'll see a bunch of these squiggly circles. And these are the kinds of things you'll see on your nano VNA. When you see those green squiggly circles going round and round, that's just the Smith chart plot of all those points that you scanned as you change frequency. Okay? And you can see that the bubble is here at 14.2. That's our analysis frequency. All right? So let's have some fun and do something really interesting. Let's first try to tune this up with a manual LC circuit on 40 meters, or rather on 20 meters, and take a look at things. 20 meters is a great place to start from. So what I'm going to do is I'm going to, I know this is my starting point, okay? And so what I think I'm going to do is I think I'm going to come down here on a conductance circle with a capacitor, and then I'm going to come up here with an inductor to come up. I think that's going to be the shortest path because I'm a negative impedance. Notice at 14.2 megahertz, I'm at minus 42 ohm. How do I know that? I can inspect it by just simply clicking on the bubble, and at 14.16 megahertz, I've got an SWR of 2.795, and I've got a Z of 1.09, which is above 2 times 50, and a negative 53 J ohms. So let's click a little closer to, that's a point on the blue chart. Okay, so that's matching up pretty darn well with what I'm seeing over here on the left of my load. Okay, so it matches quite nicely. So I think I'm going to take a strategy of bringing this down a conductance circle and up a resistance circle up here to my 50 ohms. So I'm going to need a capacitor if I'm going down, and that's a good start. And let's click on this and let's scroll this back until we get the small bubble over here, right on this resistance circle, the 50 ohm resistance circle. And then let's put in a series inductor to bring that up. And let's scroll on that and bring it up to 50 ohms exactly. And look at our SWR, 1.01. And now we've got from 1 watt, we're still 99.3% efficient. Not bad. Now the squiggles have opened up a lot. And what does this tell me? It tells me that if I'm now going to inspect this at, say, 13 to 15 megahertz, you can see the arc of all the frequencies that are within the 1.5, the 2, and the 3 SWR. And if I look at the SWR plot, you can see that there I've got 1.5 across pretty much the entire 20-meter band, and that's well below 3 SWR. And I can inspect it here by just simply clicking on it, and I can look at, see my inspection data. And in fact, look at this. It even tells me for less than 1.5, 2, and 3 SWR what the frequency range is. I think that's pretty cool. So let's solve this a different way. Let's solve this by, let's drag and drop this down into the trash. And let's drag and drop this component in the trash. That's our starting point, and we've narrowed this up from 13 to 15 megahertz. That's why we don't see all the other squiggles in there. It just makes it simpler. And now let's use the LC Auto Tuner Solver, and let's drag that up there and see what it comes up with. Wow, look at that. It came up with the same solution that we did. To go down a conductance circle, then up a resistance circle. And it comes up with the same configuration. Now, here's a fun thing you can do. I can change this from a low pass to a high pass circuit. It's a low pass because the capacitor is in a shunt mode. If I flip this around so that the capacitor was up here in series and the inductor was in shunt, I can do that by simply clicking on from low to high pass. Now it's a high pass circuit, and now I'm moving up from below the equator. I'm moving up here on a conductance circle and down a resistance circle. And if I just inspect, if I click back and forth, notice the difference between the inductor and the capacitor. In this case, the inductor is lower value than in this case. Okay, that's because I have to go travel a lot further with the inductor to bring it up to here. And that's a larger component value, which usually means a little bit more lossy. Notice the power transmitted, 99.13 versus 99.34. Okay, it's a little bit more efficient that way. And in some cases can be a lot more efficient. Okay, so let's try actually analyzing this at different frequencies. All right, so let's open our frequency range here and analyze this at, let's say, let's go to 15 meters. Okay, so on 15 meters, we can see that we are, uh, let's see, oh, I have to also change it to this to 15 meters. When you're using the auto tuner, you don't not only have to change the generator inspection frequency, but also the frequency at which you want to tune to. And then suddenly you'll see it tune up. There's my bubble, and you can see that I've tuned in very nicely. And if I zero in on 20, from say 20 megahertz to 22 megahertz, you can see I've got a very nice SWR within that range. Almost all of it is within 1.5. How do I know? Let's take a look. You can see here that if I click on the blue circle on one of these SWR circles, I'll get the analysis for all the SWR circles. So now I can see the SWR circle bandwidths for the 3 different SWR ranges I'm interested in. And once again, I can go from low pass to high pass, low pass to high pass, and inspect the efficiency. Okay. And let's try 10 meters, 28.4. And correspondingly, we have to put 28.4 in here. And now let's look at the analysis from, say, 28 to 29 megahertz. Okay, and bingo, across the entire band, we've got less than 3. And if we click here and inspect it on an SWR circle, crosses the blue line, the blue solution, a locus of solutions all across the different frequency range. As you can see, this frequency is down at 28 megahertz. This frequency is 28.99 or 29 megahertz, and everywhere in between. And if I inspect right there where it crosses the SWR circle, I get all the SWRs. And so for less than 2.0, I'm across pretty much all the good usable general single sideband portion of the 10-meter band. Now let's see how far we can push this. This would be fun. Let's see how far we can push it. Let's go to 40 meters here. 7.1, 7.1, and then let's go from 6 to 8 megahertz on our scan. And let's take a look at, all right, not bad. That's pretty decent. We're getting like half of it within a 1.5 SWR. And if we go here, we can see that we get the entire band less than 3. And if I change my center point, then I can probably tune it at center point a little bit higher. So let's do that. Let's inspect at 7.15 and let's set the tuner to solve at 7.150 megahertz. And now we can see that it's centered on the band. And now let's inspect here at this SWR circle and lo and behold, 7.020 to 7.27 or 7.287. Almost the entire 40-meter band is within 2.0 megahertz or 2.0 SWR, which is pretty darn good, right? All right, let's see if we can push this to 80 meters. So let's set this at 3.75. Let's set this at 3.75 for our tuner. And let's see what we get. Let's change the scan from 3.5 to 4 megahertz. And indeed, we get a solution. But boy, it's narrow. It's really, really, really narrow. And as I said before, you need higher and higher values. Look at the required inductor, 84.56 microhenries. I don't think there's an auto tuner out there that'll give you 84 microhenries. 1 nanofarad or 1,000 picofarad, that's doable. But 84 microhenries, you're going to be, if you can even find one, it's going to be very, very lossy. It'll be lossy and very narrow bandwidth. So this is only a 33-foot long off-center fed, remember. It's not a 64-foot off-center fed. If it were, it would be able to handle 80 meters a little bit easier, maybe down at around 20 or 30 or 40 microhenries, which commercial professional tuners can handle. Just realize, by the way, that the little AT100 by N7DDC, maximum inductance of that guy is about 8 microhenries. So that's what you're limited. So now you're seeing that you can find the limit of your tuner for any given band using SimSmith. Okay, so with that, let's move on to our next example. All right, our next example is a 40 meter, 59-foot long end-fed half wave at 50 feet. So let's go ahead and drag and drop that here. And let's go ahead and pull our auto tuner out. And well, let's do something here. Let's look at the full bandwidth scan here, 3 to 30. Okay. And let's pull our auto tuner out just to be sure so that we're seeing the whole thing. Okay, so that's our raw data. That's our raw data for an end-fed 40 meter, 59-foot long end-fed half wave up at 50 feet. Not bad to begin with, all right? So let's see how far we can push this guy. Well, we can tune the 40 meters and then we'll try tuning the 80 meter band using an auto tuner. So let's drag in our auto tuner. All right. And let's move this to 40 meters. So we'll scan from 6 to 8 megahertz. And we'll solve at 40 meters. We'll inspect at 7.1 and solve at 7.1. All right. Now we have a very nice SWR plot. And let's look at the SimSmith plot. And even within the short range of 6 to 8, we get a lot of movement. We see we've got our solution here from this starting point down and up, okay, using first a shunt capacitor, then a series inductor. Remember, left to right, inductor or load towards the rig. And look, it's only 2 microhenries. Not bad. That's very, very doable. So an end fed can be done quite nicely. You can try doing an unun with an end-fed half wave. If you've got an end-fed half wave and you scan it with your Nano VNA, capture the S1P file, import it into your PC, drag and drop it into SimSmith, and try your auto tuner, try L's and C network combinations, and try using an unun at different frequencies and see what you get. So now let's push this guy to 80 meters. Okay, let's go to 3.75 and 3.75 here. And let's see what we get for 80 meters. Boy, That's pretty tough. Let's zoom in here because we're not seeing the whole range. 3.5 to 4 megahertz. And we are, hold on, we're not quite seeing 4 megahertz. Why are we not seeing this? Oh, because we're not scanning. That's why. Here we go. We have to click on the sweep. So, and we have to engage the internal sweep on SimSmith. So, we can tune, but we're getting a 44.69 microhenry inductor. Again, that's beyond the ATU 100 and beyond a lot of lower cost auto tuners, and only the very high end will get you up in the 60s to 70 microhenry range. And let's inspect the Smith chart, and even this whole blue is the entire 80-meter band from 4 megahertz down to 3.5 megahertz. And here we are right in the middle of 3.75 megahertz, which is where our solution is. Okay, we can also see if we go to a high pass, we go the other way. All right, we can also put it into manual mode, and we can manually change and see the sensitivity. What if we only have a, say, a 30 some odd microfarad inductor available to us? Can we get into the 2.0? Well, we're just getting barely inside the 2 SWR circle with a 38 microhenry inductor. So this way we can actually inspect our solution to see if we can actually get it inside. Okay? Um, but if we go to auto mode, bang. Uh, so this is interesting to see the effect of getting our bubble. Here's our bubble, and it doesn't take much to get our bubble out of the 3 SWR circle. From here to there, we're outside and we're just inside the 3 SWR circle of the solution. So it's going to be pretty sensitive to inductor value. Let's see how it is in capacitor value. Well, I can change the capacitance value much more freely and not move my solution bubble very much at all. Okay? If I hit auto, it resolves it for me automatically. So, hopefully now you've seen some of the capabilities of SimSmith, and we're going to just continue on with the presentation here. And so I'm going to give you some exercises, but I want to give you some tips first for the exercises. Remember that component paths are added from the load or the antenna to the generator or the rig. Remember, you can mouse click to inspect the impedances on the blue curve. You don't have to click and hold, just click on it. You can change frequency ranges to zero in on the SWR range. You can change in LC values to observe the sensitivity like we just did. And then you can explore the tuner block. You can change LC values off ideal in manual mode like we just did. You can rotate the solution network and observe the LC paths and the values to see which one's more efficient. Generally, the auto tune function will come up and give you the most efficient path. You can also inspect for bandwidth and power loss in each band. So with that, I want to give you a couple exercises. So I'd like you to try to reproduce the LC path solutions manually for the following fixed impedance loads: 10, 0, 10 plus 50, 10 minus 50, 200 and 0, 450 and 0, 450 and plus 100J, 450 and minus 100J. That'll get you to get comfortable driving it around. And then solve an an off-center fed dipole with an impedance of 450 and J0, fixed impedance, using just an unun. Then add a single LRC component to see if you can get a perfect match. And then solve an end-fed half wave, where it would start with a 2250 impedance, fixed impedance with a J100, using just an unun, and then try again an LRC component to get a perfect match. So with that, I hope you enjoyed this video. Please click the like button, hit the bell icon, and subscribe to be notified for future videos. Again, this is Rudy Wiedemann, your antenna whisperer, saying 73s and have a great day. Bye-bye.